For a single-phase load, each leg can supply 1041 amps N, Bn, and Cn. When calculating the amperage for single-phase loads, you consider each phase individually. Formula is amperage equals power in watts divided by voltage times power factor. For each phase, the amperage is equal to 200,000 watts divided by 240 volts times 0.8 power factor, resulting in an amperage of 1041.67 amps. Therefore, each phase N, Bn, and Cn can supply approximately 1041.67 amps. This value is significantly higher than the 348 amps that the generator can supply for a three-phase load. This difference arises because three-phase power distributes the load across multiple phases, thus reducing the current drawn on each individual phase. Understanding the distinction between single-phase and three-phase load calculations is crucial for ensuring the safe and efficient operation of your generator. It is important to know how much current each phase N, Bn, and Cn can handle. For a 200 kilowatts generator operating at 50 Hz with a 415/240 volts configuration and a 0.8 power factor, the three-phase amperage capacity is determined by dividing the total power by the product of the voltage, the square root of 3, which is 1.73, and the power factor. The single-phase amperage capacity per leg is calculated by dividing the total power by the product of the single-phase voltage and the power factor. When dealing with a three-phase load, the generator's output is distributed across all three phases, resulting in a lower amperage per phase compared to a single-phase load scenario where the entire load is concentrated on one phase at a time. Therefore, a single-phase load connected to one leg of the generator can draw a significantly higher amperage than what each phase would handle in a balanced three-phase configuration. To prevent overloading the generator, it is essential to stay within the specified amperage limits for both three-phase and single-phase loads. Exceeding these limits can lead to overheating, voltage drops, and potential damage to the generator or connected equipment. Always refer to the generator's specifications and consult with a qualified electrician to ensure proper load balancing and safe operation. The power factor, represented as 0.8 in this case, plays a crucial role in determining the amperage. A lower power factor indicates a less efficient use of electrical power, resulting in a higher amperage draw for the same amount of power delivered. Power factor correction techniques can be employed to improve the power factor and reduce the overall amperage demand on the generator. These techniques involve adding capacitors to the electrical system to offset the reactive power caused by inductive loads such as motors and transformers. By improving the power factor, the generator can operate more efficiently, deliver more usable power, and experience reduced stress on its components. The frequency of the generator, which is 50 Hz in this scenario, is another important factor to consider. The frequency affects the performance of certain electrical equipment, particularly motors and transformers. Ensuring that the generator's frequency matches the requirements of the connected equipment is crucial for preventing damage and ensuring proper operation. The voltage configuration of the generator, which is 415/240 volts, indicates the line-to-line voltage, 415 volts, and the line-to-neutral voltage, 240 volts. The line-to-line voltage is the voltage between any two phases, while the line-to-neutral voltage is the voltage between any phase and a neutral conductor. Single-phase loads are typically connected between a phase and the neutral conductor, utilizing the 240 volts voltage. Three-phase loads are connected across all three phases, utilizing the 415 volts voltage. When connecting loads to the generator, it is important to ensure that the voltage requirements of the loads match the generator's voltage configuration. Connecting a load with a different voltage requirement can lead to damage or malfunction. The kilowatt rating of the generator, 200 kilowatts, indicates the maximum power output that the generator can deliver. This rating is typically specified under standard operating conditions and may vary depending on factors such as temperature, altitude, and humidity. When selecting a generator for a particular application, it is important to choose a generator with a kilowatt rating that is sufficient to meet the anticipated load demand. It is also advisable to provide some margin for future load growth. Proper maintenance of the generator is essential for ensuring its reliable operation and longevity. Regular maintenance tasks include checking and changing the oil, cleaning or replacing the air filter, inspecting the spark plugs or fuel injectors, and checking the battery. A well-maintained generator will provide years of dependable service and minimize the risk of unexpected breakdowns. The location of the generator should be carefully considered to ensure proper ventilation and to minimize noise pollution. Generators produce exhaust fumes that contain harmful gases such as carbon monoxide. Therefore, it is important to locate the generator in a well-ventilated area and to avoid operating it indoors or in enclosed spaces. Noise pollution can also be a concern, especially in residential areas. Measures can be taken to reduce noise pollution, such as installing a sound enclosure around the generator or locating it away from sensitive areas. Safety precautions should always be observed when operating a generator. These precautions include wearing appropriate personal protective equipment such as gloves and safety glasses, avoiding contact with live electrical components, and following the manufacturer's instructions for operation and maintenance. It is also important to have a fire extinguisher readily available in case of emergency. The generator should be grounded properly to prevent electrical shock hazards. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker and energizing the circuit. The grounding conductor should be connected to a grounding electrode such as a ground rod or a metal water pipe. The size of the grounding conductor should be appropriate for the size of the generator and the expected fault current. Overcurrent protection devices such as circuit breakers or fuses should be installed to protect the generator and the connected equipment from overloads and short circuits. The overcurrent protection devices should be sized appropriately for the load and should have a current interrupting rating that is sufficient to handle the maximum fault current. Surge protection devices should be installed to protect the generator and the connected equipment from voltage surges caused by lightning strikes or other electrical disturbances. Surge protection devices divert the surge current to ground, preventing it from damaging sensitive electronic components. Automatic transfer switches can be used to automatically switch the load from the utility power to the generator power in the event of a power outage. Automatic transfer switches provide a seamless transition, minimizing downtime and preventing damage to sensitive equipment. The automatic transfer switch should be sized appropriately for the load and should be installed by a qualified electrician. Remote monitoring systems can be used to monitor the generator's performance and to receive alerts in the event of a problem. Remote monitoring systems can track parameters such as voltage, current, frequency, power factor, and fuel level. Alerts can be sent via email or text message to notify the operator of any issues. Understanding the various aspects of generator operation and maintenance is crucial for ensuring its safe and reliable performance. By following the guidelines and recommendations provided, you can maximize the lifespan of your generator and minimize the risk of unexpected problems. Consulting with a qualified electrician is always recommended for any electrical work related to generators. A qualified electrician can ensure that the generator is installed and operated safely and in accordance with all applicable codes and regulations. The specific calculations for single-phase and three-phase amperage depend on the generator's configuration and the characteristics of the connected loads. It is essential to use the correct formulas and to consider all relevant factors to obtain accurate results. The information provided is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or engineer for specific recommendations related to your generator and electrical system. This is to provide more context to the calculation. The 200 kilowatts represents the generator's total power output capacity. When supplying a three-phase load, this total power is distributed across the three phases. For a single-phase load, the entire 200 kilowatts capacity is, in theory, available to be drawn from one phase. However, practical limitations and the generator's design may prevent you from actually drawing the full 200 kilowatts from a single phase without causing imbalance or other issues. The 415 volts is the line-to-line voltage in a three-phase system. This is the voltage measured between any two of the three phases, such as between phase A and phase B. The 240 volts is the line to neutral voltage. This is the voltage measured between any one phase, such as phase A, and the neutral conductor. Single-phase loads are typically connected between one phase and the neutral, hence the use of 240 volts in the single-phase amperage calculation. The 0.8 power factor represents the ratio of real power, kilowatts, to apparent power, kilovolt amperes. It indicates the efficiency of the electrical system. A lower power factor means that more current is required to deliver the same amount of real power. This increased current leads to higher losses and can strain the generator. Understanding the power factor is crucial for optimizing the performance of the generator and minimizing energy waste. It is also important to consult the generator's documentation or a qualified electrician for the specific single-phase loading limitations. Generators are often designed with limitations on how much load can be placed on any single phase to maintain balance and prevent overheating or other problems. Remember that these calculations provide theoretical amperage values. Actual amperage may vary depending on factors such as the load characteristics, wiring impedance, and other conditions. Always use appropriate measuring instruments to verify the actual amperage and ensure that it remains within safe limits. If the single-phase load is significantly unbalanced, it can cause problems such as voltage imbalances, increased neutral current, and potential overheating of the generator windings. Balancing the load across the three phases as much as possible is always recommended to ensure optimal performance and longevity of the generator. If you have a large single-phase load, consider using a three-phase transformer to convert it to a three-phase load and distribute it more evenly across the generator's phases. Additionally, regularly inspect the generator's wiring, connections, and cooling system to ensure they are in good condition and functioning properly. Over time, connections can loosen, wires can become damaged, and the cooling system can become clogged, all of which can affect the generator's performance and reliability.